So now we're going to apply boundary conditions, step 5 in our process here, boundary conditions and load. So we got our picture here in the upper left, so we can refer back to that. Here's the setup here. So we got the global stiffness matrix times the displacements times the loads. And boundary conditions here, we have the pin joint restricts us, so we have no displacement at node 1 in the x or y direction. So because we have no displacement in the x direction, we can knock out the whole first row and the whole first column. Now we could change this to 1 and make everything else zeros, but the easier thing, at least when we're doing this in Mathcad, is to just wipe out these rows. So we can do that. And then we can also, there's no displacement in the y direction, again, because of the pin joint. So those can go. And then no displacement in the y direction because of the roller joint. So those can go. So because these are all equal to 0, we can eliminate the first, second, and fourth rows and columns. Right? And so we can just whittle it down to just the 3x3 stiffness matrix, because the other ones we just ignore. We know they're 0. So we're not going to try to solve for them. We also have our load of 100 pounds. And the 100 pounds is acting in the global x direction, right? Globally in the x direction at node 3. So that's why we apply 100 pounds right here. And that's why we needed the global form. We couldn't have done this in the local form because it's not being applied in this direction. This is really all when we're saying these members are only 2 force members, we have to apply this on a global scale. We can't really apply it on a local scale. I guess we could have broke it into components and do it that way, but we'll see how that works out here. All right, so how do we do this? How do we whittle this guy down, take out these rows and columns, and get to what we want to do? Well, we use what I'm calling the boundary condition matrix. It's another transformation matrix, but we only include what we want to keep. Right? So what we want to keep is the displacement at node 2 in the x direction. We want to keep displacement at node 3 in the x and y direction. So there's a 1 here, here, and here. So it's a 6x3, 6 because we have 6 different coordinates between our 3 nodes. And then it's a 3 because those are only 3 displacements that are left to solve for. All right, so there's the u2x, displacement at node 3 in the x, and then displacement at node 3 in the y. So we can reduce that matrix down to this, which I'll show you here how to do in a sec. Right, and we can solve that linear system of equations and come up with these values for our displacements. All right, so let's go do that. All right, so we're going to apply boundary conditions. All right, so boundary conditions, again, said it was a 6x3. So we'll get up our 6x3 matrix here. And we want to keep the displacement at node 2 in the x direction. So that's here. So these first two are for node 1. And we also want to keep node 3 in the x and the y direction. All right, and then we'll backfill with zeros. All right, so that looks good. So the reduced form of our global stiffness matrix, so the sub R here stands for reduced. The reduced form, how we get that is we're going to take the boundary condition matrix. We're going to take the transform of that times our global stiffness matrix in global form times, again, the boundary condition matrix. So instead of developing it into the global form, we're kind of hacking it back using the same process. All right, and again, fixing the dimensions, or sorry, the dimensions, units. All right, so we get that form, so that looks good. Now let's look at our force matrix. So this is our 1/6, and so it was 0, 0, 0, 0, and it was 100. So at node 3 in the x direction and 0. And we want to cut that guy down too. And the way we do that is we're going to put in the boundary condition matrix, the transform of that, times our global force matrix equals that. All right, so we keep just the force playing node 3 in the x direction as well as the other two displacements that we're interested in. All right, so let's get down to the solution phase here. We'll expand this section here. All right, so we're looking at finding the displacements in our reduced form. So we got Kg sub r, so our stiffness matrix. And to solve a linear system equation, we take the inverse of this and multiply that by, -1, and then arrow forward to get out of that superscript, times the global force matrix in the reduced form. And we solve for, our values in inches. Let's see what happened here. Oh, I forgot to label these up here. Make sure I add this up here. We need a label for units on their force. So I'm going to click just outside the matrix there. You see it blinking there. So call that pound force and enter. See, this updates to newtons. We'll fix that to pound force. And sliding down here, that fixed itself right up. So that's in inches. Good. All right, so making sure we got units all the way through. All right, so again, this is the reduced form, and then just to put that back into a global form where we can see the displacements of all the different coordinates or components at all the different nodes. We're going to multiply times the boundary condition matrix times the reduced displacements matrix. And we get that. So we get our 0, 0 displacements and 0 at node 1 and node 2 in the y direction, and then we get the other ones that we developed over here. All right, so that all looks good. All right, so now step 7 is we want to obtain some other information. We don't want to just have the displacements. We also want to find reaction forces, stresses. All right, so to get the reactions, as we looked at before in the direct formulation lecture or presentation, we have the reactions are equal to the global stiffness matrix times the displacements minus the forces. All right, and here's our reaction matrix. And we can perform those matrix operations and solve for the reaction forces. And just to do a sanity check, does this make sense? We got 100 pounds being applied in the x direction. We should see 100 pounds reaction force because this is the only point preventing this thing from sliding in the x direction. So we see a negative 100 there being applied at node 1. So that looks like we're on the right track there. All right, so let's do this. All right, so come down here, we're going to post-process with our reaction forces. So we got R, and that's going to be equal to our global stiffness matrix times our global displacements minus the global forces. And that equals our matrix, and updating the units. And right there. All right, so that looks good. And you're going to see this a lot as we go through this. It's not come out to just 0, but it's 10 to the minus 15 is essentially 0. So just heads up for that as you look at the results in some cases here. All right. Come back here. Let's look at our internal and normal stresses. So for each element, we have already got the global displacements, and those are going to be equal to the transformation matrix times the local displacements. So we have these, we want to get these. So to do that, we multiply both sides by the inverse of the transformation matrix to work ourselves back. So we got the global displacements multiplied by the inverse of the transformation matrix. We can find our local displacements. All right, so local displacements can be found for each element since the angles and the global displacements are known. And so once we know the global displacements, we can figure out the force. And if we know the force, we can get the stress. So if we got force divided by the area gives us stress. And because the force is equal to the change in displacements times K, we can plug that into the numerator. K we know is AE over L. And solving A is going to cancel out. So stress is basically the modulus times the change in local displacements all over L. All right. So note these signs. The signs we have for a negative sign in front of the I x component and a positive sign in front of the node J x component. It's so that we get tension. A positive value indicates tension and a negative value indicates compression. So that's why those values are as they are. All right, so element 1, local displacements. So we're going to start with our plugging our global displacements and our inverse transformation matrix. And so here's our global displacement, 0.05 inches that we found at node 2 in the x direction and 0 everywhere else in our inverse transformation matrix. Solve that for the local displacements, and hey, it comes out to 0.05. Now this is because the angle here, if you remember for element 1, the angle is 0. So that's why it doesn't change between the local and the global coordinates. All right. For local forces in element 1, all right, we're going to plug in our stiffness matrix for our element times the local displacements we just found. We can figure out the local forces. And we get the local forces at x in the node I, and x in node j is -50 and 50 pounds. Looks good there. So finding the internal stress, all right, we got the local displacements, and we can substitute in for those and come up with 500 psi. It being positive, it is in tension, so the T stands for tension here. We can also do this for elements 2 and 3. All right, so for element 2, we plug in for our inverse transformation matrix and our global displacements here on the right. Solve for the local displacements. Same thing for element 3. Now we're at 60 degrees for this element, and we have the local displacements there. And solving for the local forces. Right, so substituting for the K matrix and local displacements. Again, K is the same for all of our elements at this point. So we got 100 pounds there at node 2 in the x direction, negative 100 pounds at the node 3 in the x direction, and element 3, you can solve for those forces again, negative 100 and 100 pounds. So when we plug this into our stress, we have our stiffnesses in the x direction, and that comes out to be having compressive load in node 2, or element 2, excuse me, and tension load in element 3. And that's what we expect if we had the triangle like this, and we had the load being applied this way. We'd expect tension to happen here in element 3. We'd expect compression here in element 2, and we'd expect tension in element 1, which we had. All right, so that concludes this presentation. I didn't get a chance to show you how to do the elements, finding the stresses and stuff in Mathcad, so I'll leave that as an exercise for you, and I think we'll actually end up covering that in the future presentations. So let me know your thoughts in the notes or the comments below, and hope to see you for the next one.